Welcome to my channel Phi Concepts CHM. This is the third part of the series of electrical properties of metals. Here we will see the quantum theory of free electrons, introduction to quantum statistics, Fermi distribution function. Quantum theory of free electrons. Classical free electron theory of metals was developed earlier than the quantum theory, which explains most of the properties of metals. Failures of classical theory are inability to explain discrepancy between the observed and predicted electronic specific heats of metals. Second, every electron has magnetic moment associated with its spin and classically should give rise to paramagnetic susceptibility inversely proportional to temperature. While experimentally, paramagnetism in metals is independent of temperature. Errors were removed by Sommerfeld in 1928, who applied the Fermi-Dirac statistics in place of Maxwell-Boltzmann statistics used by Lorentz. Distinction between classical theory and quantum theory. In classical theory, it assumes that all free electrons can absorb energy. Quantum theory says 1% of free electrons can absorb energy. Classical theory does not agree with the experimental values. In quantum theory, specific heat and magnetic susceptibility values are in better agreement with experimental values. Classical theory is based on Maxwell-Boltzmann statistics. Quantum theory is based on Fermi-Dirac statistics. So quantum theory was given by Sommerfeld. He retained the concept of free electrons moving in uniform potential within a metal, as in classical theory, but treats the electrons as obeying laws of quantum mechanics instead of classical mechanics. Later, when periodic nature of crystals was known, it was modified. Hence, the field experienced by the free electron is said to be periodic in nature. The theory lays restrictions on free electron energies inside the metal crystals, as allowed energy levels of electrons are bound to a single atom, that is, they are quantized. The electron is also prevented from leaving the crystals. The electron is prevented by the potential well at the ends of the crystals. That is, the electrons are trapped in a constant potential well. In this theory, permissible energy levels can be obtained by solving the Schrodinger's equation. Distribution of the electrons in various permissible energy states can be obtained by the Fermi-Dirac distribution. Quantum theory also has drawbacks. It cannot explain why some crystals have metallic properties and others do not. Introduction of quantum statistics. In Maxwell-Boltzmann statistics, particles can be distinguished from one another. It is assumed that the wave functions do not overlap. In Fermi-Dirac statistics and Bose-Einstein statistics, particles are indistinguishable. The wave functions overlap. Bosons and fermions have different distribution functions. Bosons. Particles with zero or integral spin, that is 0, 1, so on. Example, photons, phonons, alpha particles, pi mesons, etc. They do not obey Pauli's exclusion principle. That is, in a given state there can be more than one boson. The wave function of a system of bosons is not affected by the exchange of any pair of them. That is, it is symmetric. Fermions. Particles with half integral spin, half, 3 by 2, so on. Example, electrons, protons, neutrons, etc. They obey Pauli's exclusion principle. That is, in a given quantum state, there is only one fermion. The wave function of fermions changes sign on interchange of any pair of them. That is, it is antisymmetric. Fermi distribution function. Probability f of E that a fermion occupies a state of energy E is given by Fermi-Dirac distribution function. It's given as f of E is equal to 1 upon e raised to alpha into e raised to e by kt plus 1. Equation number 1. Alpha depends on properties of particular system. It may be a function of temperature. Plus 1 term in the denominator in equation 1 is a consequence of uncertainty principle. That is, no matter what the values of alpha, E and T, f of E cannot exceed 1. If E is very much greater than kt, the Fermi-Dirac function approaches Maxwell-Boltzmann statistics. For f of E is equal to half, substituting f of E is equal to half in this equation and rearranging the equation such that e raised to alpha into e raised to ef upon kt plus 1 is equal to 2. Note that in place of e we have taken e suffix f, which we will see what it is. Taking 1 on the other side, the equation becomes e raised to alpha into e raised to ef upon kt is equal to 1. Adding the two powers, this becomes e raised to alpha plus e suffix f upon kt is equal to 1. Taking log on both sides, this becomes alpha plus e suffix f upon kt is equal to 0, and from this you get alpha is equal to minus e suffix f upon kt. Therefore, we get e suffix f as minus alpha kt. Equation 2. This is the Fermi energy, a very important quantity in a system of fermions. Substituting this alpha in the Fermi distribution function, we get the f of E is equal to 1 upon e raised to minus ef upon kt into e raised to e by kt plus 1. Finally, f of E is equal to 1 upon e raised to e minus ef upon kt plus 1. Equation 3. Using equation 3, we get two cases. We will consider at a temperature is equal to absolute 0, T is equal to 0 and E is less than EF. Substituting these values in this equation, as T is 0, this term becomes infinity, and as E raised to E is less than EF, so it becomes minus infinity. So 1 upon e raised to minus infinity plus 1. E raised to minus infinity is 0. So this finally comes as 1. In case 2, again at t is equal to 0 and e greater than ef, the power becomes infinity plus infinity, and e raised to infinity is infinity. So this is 1 upon infinity, that is 0. Using these values, we can plot a graph of this kind. For E less than EF, f of E is 1, and for E greater than EF, f of E is 0. Therefore, at T is equal to 0 Kelvin, all energy states up to EF are occupied, and none above EF are filled. In figure 2, at T greater than absolute 0 but with KT less than EF, fermions will leave state just below EF. This curve for T greater than 0. So the fermions will leave the state just below EF and will move on to the states just above it. At still higher temperatures, E1, the lowest state will be excited to the higher ones. That is, this curve for T is equal to infinity. F of E in this case will drop below 1. Thank you for watching my video.